Welcome to class. In this lecture, we're going to talk about using logic to reason about your programs. In particular, I'll introduce the concept of an invariant. An invariant is a logical condition that holds repeatedly at certain points during the evaluation of your program. Now, we already have some invariants that we're aware of in this class. Here's a classical one. Scott wears ties. Now, the critical thing to note about this invariant is that it holds when Scott's shooting a video. It also holds when Scott's at work, but it doesn't have to hold all the time. For example, I'm pretty sure Scott doesn't wear a tie when he's taking a shower, at least I hope not. For invariants for your program, it'll be the same thing. An invariant will hold at one point during the program. There'll be some computation, the invariant will hold again. Be some more computation, the invariant will hold again. So the critical thing is the invariant doesn't have to hold after every statement, but it has to hold repeatedly as your computation advances toward an answer. We'll look at some examples and some definitions, and I'll show you how we can use invariants to help basically build better functions and reason about the correctness of your program. An invariant is a logical condition that repeatedly holds during the execution of your program. So here, just a logical condition you can just think of as a Boolean expression that involves the variables in your program. I'm going to use invariant of something to represent this expression for these notes. So this condition should hold as your program executes. And in fact, if we kind of label the points where it holds, P1, P2 up to Pn, then we can actually kind of express the relationship between the condition and the portions of the execution trace for your program in the following way. So if I let fragment I correspond to the portion of the trace between the points pi and pi plus 1, then we can split the trace of the program up into pieces and then kind of add assertions that reflect the fact that the invariant has to be true. So here are the fragments, fragment 0, fragment 1, fragment 2 up to fragment n. Those are the parts of the trace. What we've done is we've added assertions here that say that the invariant is true between these fragments. So what you can see here it is, it's run some code, check the assertion, check the invariant, run some code, check the invariant, run the code, check the invariant. So we're seeing that the invariant is true at multiple points during the execution of the program. Now you're probably asking, well, why the heck are we bothering with this? What does it do? Well, a well-designed invariant can help us do two things. It can guide us in building pieces of our program. It can also help us verify that our program is actually doing what we expect. I mean, notice here, for example, if I know the invariant, if you give it to me, I know when I write this piece of code for fragment 0 that it has to actually guarantee that the invariant holds after we execute fragment 0. Let's think about how we would actually build fragment 1. Fragment 1 can rely on the fact that the invariant is true whenever we begin executing fragment 1. And then we have to make sure that after we finish executing fragment 1, the invariant is true again. So this gives us insight into how to design these fragments of code. The other thing is that it allows us to reason about the correctness of the program. Kind of reasoning about all these invariants at once is difficult, but notice here we've kind of isolated it down to pairs of consecutive invariants. Okay. If we assume that the invariant is true, say before we start executing fragment I, we can use that fact when we're actually executing fragment I to then try to derive that the invariant is true after execution of fragment I. So we can chain all these assertions together to reason about the entire program. That'll be very valuable. All right, the previous description was fairly abstract, so let's get our hands dirty and look at a really concrete example. So I'm going to talk about invariants for loops. So the idea is that we're going to build an invariant that's going to help guide us in both writing the code for a loop and then verifying that the loop produces a correct answer. So here I've got a function. It computes the factorial function. It's kind of our favorite test function. And we've actually already designed an invariant for it. So we're going to have a local variable answer and a local variable index. And we want to make sure that our invariant is that answer always holds factorial of index. So a couple of things to note here. This invariant doesn't hold after every statement is executed. It only holds where I've actually put these assert statements. Okay, we talked about code fragments up here. So when we're evaluating this function iterative factorial, kind of the first code fragment is we set answer to be 1 and index to be 0. So we now like for this invariant to be true, the invariant that answer is equal to factorial of index? Well, let's see. Is 1 equal to factorial of 0? Yes, it is. So good, we've made sure that the invariant holds now before we start trying to execute this while loop. So now what's the next fragment of code we're going to execute? We're really going to execute the body of this while loop. We're going to repeatedly execute the fragment of code that corresponds to, we increment the index and we take the answer and multiply it by the new index. So what we'd like to do is if we start off before we execute the body and we know this is true, we'd like to then verify that the invariant holds after we execute the body of the loop. And so the thing to note here is that before we execute answer is equal to factorial of index, we now increment index by 1. We make it 1 larger. So what do we need to do to this running product that we're computing for the factorial? We better multiply it by this new value for index. So if we do that, we're guaranteed now that the new answer, again, contains the updated factorial. The final thing to note here is that this factorial then allows us to reason about the correctness of this loop. When does this loop terminate? The loop terminates when index is equal to num. So if index is equal to num, then we conclude that the answer is just math.factorial of num. Our loop actually correctly computed factorial. All right, let's look at this function inside Code Sculptor. So here's my iterative version of factorial. We have 2 assert statements that contain our invariant. And if we run that, sure enough, it says the 4 factorial is 24. That's awesome. Now, I talked about the interplay between building these fragments of code and checking that the invariant is true. Let me show you an example of how this can help. Let's say I was writing my initialization for my loop and I made a silly error. I initialized answer to be 0. As I run this, the invariant is violated immediately before entry on the loop. In particular, 0 is not equal to 0 factorial. We could also use this to check to make sure that the body of our loop is doing what we expect. Let's run this and maybe have it do a sum instead of do a product. And sure enough, again, we get an error here that says we violated this invariant. So even if you're really not reasoning about your program, you can use the invariant to check to make sure that the code you've written is doing what you intended. Let's go on down and I'll show you a few more examples in this file. Here's one where I've annotated merge with an invariant. The invariant is that the answer is sorted. You notice it's actually, we're asserting this at various places during the program. I've actually gone through and annotated 2 recursive functions with an invariant. In this case, that basically the recursion is computing the correct value for factorial. Down here, I have an invariant that merge sort is returning a sorted answer. So again, I'm really not doing a lot of reasoning here, but I'm just going through and adding invariants in to check that my computation is proceeding the way that I expected. Okay, let's look at one more example, and I'll go back to the notes where we'll talk a little bit about how we can use invariants inside classes. Now let's talk about how invariants can apply when we're building classes. So if you recall back when we worked on breadth-first search, we had a wildfire demo that kind of explained breadth-first search in terms of a fire spreading. In the class that I built for this wildfire demo, the objects that I built had both a boundary queue and a grid. And the boundary queue was designed to kind of model the boundary of the fire as it burned. And during the use of that class, I always maintained the following invariant. Then whenever we added a cell to the boundary queue, we always set the corresponding cell in the grid to be full. That kept us from adding that cell back into the boundary queue a second time. So that was actually an invariant. I never actually explicitly formulated or tested that or anything like that, but we can actually update our implementation of the wildfire class to actually explicitly capture that invariant. Now, the condition that we're going to build is going to be complicated because it's going to involve all the cells in the boundary queue. So in that particular case, we may not be able to write a single expression, but we could actually build a method that captures that invariant. So here's a method called boundary invariant. It takes all the cells in the fire's boundary and then checks to see if that cell is empty. If it's empty, we've violated the invariant. So what we do is we print out a message to say something went wrong, and then we return false. If all the cells are full, then everything's good. We return back true. So this method now actually captures the invariant for our wildfire class. So let's go look at the code for a little bit. All right, let's finish off class and look at a slightly modified definition for the wildfire demo. So here's the class definition. If I scroll down to the bottom, you can see probably the two most important methods. This is update boundary. This did one step of breadth first search. And this method, boundary invariant, checks to make sure that every cell on the fire's boundary is also set to be full. If it detects one that's empty, it prints out an error message and returns false. So I've gone through and I've actually added that invariant to update boundary. I want to check and make sure that this is true. And in fact, you can see that I kind of guarantee it's true by just having two statements here. If I add anything to the fire's boundary, I go through and also set the corresponding grid cell to be full. We can run this and it's all good. I'll start doing some BFS and no problem. Let's just double check and make sure that it's actually doing what we expect. Let's go through and actually just comment out the statement that sets the corresponding grid cell to be full. So if I run that, sure enough, I get an assertion error here. I added something to the boundary and the corresponding cell was empty. Now this leads to kind of an interesting observation. As I thought about this example, I was thinking, is my class definition always guaranteed to make this invariant true? Let's scroll up, because I think I have a method called enqueueBoundary, and that just lets me throw something in the boundary queue. Now in the version that I had for my initial implementation, this was all there was. What happened was when I called this an update boundary or inside the GUI, I always did a corresponding set full for that grid cell. In other words, I relied on the user to make sure that the invariant always held. Probably a better design would be to just design the class so that the invariant is always true. Don't rely on the user. The user is going to screw up. Just if it's an invariant, make sure it's true. So here's what I've done. I've gone through and I've set the corresponding cell to be full, and then I've asserted the boundary invariant again. So this version of the class now has the property that I can't violate it by doing enqueueBoundary. Now I could still violate it by doing, say, maybe set empty for one of the grid cells. So I need to consider that also. But the thing here is not whether this was correct or incorrect. It's the fact that by formally expressing an invariant for the class, it made me think about how I built my class methods. And so it exposed some of the corner cases that might trip me up whenever I'm trying to either debug the class or when I have a user who hasn't really talked to me a lot use the class. So the upside here is that by thinking about invariants in a more formal manner, you can improve the quality of the code that you're writing.